thank you for listening to my talk. I'm excited to talk to you about work that I did at the end of my thesis called How Trustworthy is Your Tree? Bayesian and Phylogenetic Effective Sample Size Through the Lens of Monte Carlo Error. There's a preprint of the same name if you're interested in more details. This is work I did with Mike Carter, Eric Mattson, and Vladimir Minin. I want to take a brief moment to thank my funders, including the UW Department of Biology, where most of this work was done. Now, our outline today. First, I want to make sure we're all on the same page about phylogenetic models and therefore why an ESS for trees is difficult. Then I want to talk about how we can assess effective sample size measures and whether they work, then how we might compute them for trees, and then put all of this together and definitively answer the question, are there effective sample size measures for trees? So, phylogenetics. The core object in phylogenetics is a phylogeny, sometimes called a phylogenetic tree. A phylogenetic tree topology is the part of that that specifies a series of nested relationships. So here is a tree. The topology tells us that humans and dogs are more closely related to each other than either are two birds. This is a nested relationship. We also have a nested relationship here. If we compare teal to purple, we see that humans, birds, and dogs are all more closely related to each other than they are to frogs. So a tree contains many such nested relationships. And more tips in the tree, more species, more relationships. So it's this big sort of combinatorial object. I'm going to use the words tree and topology basically interchangeably today, though that's not always a great idea in the literature. And note that there's also a time component here, right? We have branch lengths, and those tell us about how much evolutionary change has accrued on these different parts of the tree. So often we're just going to work with trees that look like this, and this is what we're going to work with today. These are called unrooted trees. They are easier to do inference on because they have fewer constraints. The nice thing about an unrooted tree is that if you know something about it, like crabs do not belong in the rest of those species we just saw, we can pull out the root there and we can recover a rooted tree on the group of species we care about. This is called outgroup rooting. Okay, all that aside, phylogenetic models. Start with the tree topology that specifies the relationship, add branch lengths that specify the time component for evolutionary change. The model for that change is a continuous time Markov chain model. Here I'm showing you an illustration of what this model might look like for DNA data. So we have nucleotides, A, C, G, and T, and we have rates of change between these things. And so the model that specifies those rates of change allows us to, along this tree, specify character histories of what all the states were in all of the different parts of the tree. Now, we can't observe internal nodes. Those are things that have gone extinct. So we end up with sets at the tip. We collate those into what we call a multiple sequence alignment. And then we draw IID a lot of columns from our model, independent, conditional on the tree and these branch lengths. And so that is our graphical model for our data. That gives us this posterior distribution on trees and CTMC parameters given the data. We, of course, have a phylogenetic likelihood. We have priors on the trees. We generally assume all topologies are uniformly a priori likely. And we have some priors on our rate parameters. Now, for diagnosing MCMC performance, the CTMC parameters are pretty easy. They're continuous. The tree is not continuous. It is high dimensional, combinatorial, and altogether weird. So what are we to do if we want to know if our tree sampling worked well and if our estimates are trustworthy? Well, one thing we can do is follow along with the suggestion from Lanphier et al. 2016, where they suggest an effective sample size for trees. What they did is introduce two different distance-based approaches, and then they showed that these correlate with things that an ESS measure should. So if you increase the length of the chain, you increase the effective sample size. If you have multiple modes and you switch between them more often, you increase the effective sample size. Now, an ESS should have properties on that order, but that's not really a definitive demonstration that these work, which leaves some questions. Do they work? Are there other approaches that work? And I think kind of the crux of the issue, how would we know if these measures are working? So let's take a step back to ESS in the simpler case of a one-dimensional Euclidean random variable. The effective sample size allows us to, at least in the asymptote, quantify the standard error of the mean. So we have n MCMC samples, we estimate the mean mu hat. The standard error of that mean is given by the posterior standard deviation divided by the square root of the effective sample size. Now, you may be more familiar with this slight rewriting of things. So in this case, we say the variance of the mean over the true sample size is the posterior variance over the effective sample size. They're just interchanges of the same thing. Now, from this, or rearrangements of it, we can figure out how to compute this from theory, and we end up with something that looks like this: an effective sample size in terms of the true sample size and this telescoping sum of lag t autocorrelations. That's great, but what about trees? Well, to me, this relationship suggests a way that we might test any ESS measure in simulation. Let me try to show you what I mean. Both of these are estimates of the standard error, right? They're estimates, so they might not be exactly equal, but if we had a way to estimate the standard error both ways with MCMC chains and effective samples, then we could test if the effective sample size measure worked. That might look like this. Run one MCMC chain, and then another, and then a bunch more on any variable you want. Then, for each of these MCMC chains, compute the effective sample size, draw that many samples IID from the true posterior, and then do it again for each of the chains. So now we have a bunch of MCMC samples and a bunch of should be equivalent IID samples. Compute the means, get rid of everything else, pile them up, compute the standard errors. If the ESS measure works, we should find that these standard errors are basically the same, because what we've done is measure the standard error by drawing a bunch of MCMC chains of length n with true MCMC SD of the mean, and then draw a bunch that are equivalent with the posterior variance. So if it works, those two quantities should be the same. Now, let's sort of generalize and write this out a little more specifically. A general way to test ESS measures. Run a bunch of MCMC chains, say M. Collect some number of samples from each. You can thin if you like. We're going to thin all of the tests we do to 1,000 samples because we're going to have to compute distance matrices for every MCMC chain. And once you start moving to 10 or 100,000 samples, that's a lot of distances to compute. Now, for each of these chains, we're going to pile them up, and we're going to use that to estimate the Markov chain Monte Carlo standard error. We're going to call that the SE MCMC, and we're going to move beyond means into any summary you want. We'll just call that S of M. So not just a mean, could be anything. For each of those chains, compute the effective sample size, draw that many samples IID from the true posterior. That gives us, by pooling those chains and looking at the variance, that gives us an equivalent, the effective sample size equivalent Monte Carlo standard error. Then compare them. They should be estimating the same thing, so they should be the same. That's our approach. Okay, well, how are we summarizing trees? We're going to look at three different things. I'm going to focus on the first of these today. So we have a bunch of tree samples. The thing I'm going to focus on is called a split probability. A split or bipartition is simply a division of the tip set in half, or well, in two parts. Some of them are on one side, some of them on the other. The posterior probability of that, which marginalizes over the bits of topology on either side, is support for the relationship. So if you're interested in knowing whether humans go with dogs or with frogs on that tree we saw earlier, posterior split probability gives you that. Okay. Sometimes we just want posterior probabilities of specific tree topologies. Maybe we have very specific hypotheses or something else. Well, we can use those as summaries too. These are both very high dimensional summaries. One posterior distribution has many splits and many trees. And whenever you look at a tree in a paper, right, you're seeing a summary tree of some form. The authors have chosen a tree to stand in for the posterior. So we might want to know how well we are doing at variability in that summary. Okay, before we move on, I just want to sort of recap the good, the bad, and the weird of this empirical testing setup that we're taking. I think the bottom line is that we've turned what is a difficult theoretical problem into smaller and actionable pieces. So we've taken this notion of an ESS for trees, and we've broken it down into, first, how do we compute one? And second, how do we assess if it works? The first question allows us to be creative and try a bunch of things. The second one, if we ground ourselves appropriately in theory, allows us to make sure that we don't go overboard and that those things work. Of course, like I keep saying, this does require us to draw IID samples from the posterior, but this really isn't any sort of deadly limitation. In the paper, we show in some detail how you can convincingly fake MCMC on an empirical posterior distribution. What this boils down to is that a distribution on trees is basically a categorical distribution. MCMC induces a graph on that categorical distribution. So if you have one that you've inferred, you can draw samples categorically from it. That's the IID bit. And you can run MCMC on that graph. That's the MCMC bit. And so you can compare those two things. Okay, now how do we actually compute these effective sample size measures? Well, we're going to follow Lanphier, and for the most part, we're going to use distance-based matrices, distance matrix-based approaches, and that's all I'm going to show you today are those. We have a distance matrix, dij, distance between the I and j samples. Now, there's a lot of ways to compute distances between trees. We're going to use the Robinson-Folds distance, which looks at trees as a collection of splits. This is natural because splits are one of the things we're most interested in, but also because several algorithms for, say, summary tree production have to do with splits or can be viewed that way. So this is tied to things that we're interested in. Okay. Among the two approaches they suggested, the approximate ESS and the pseudo-ESS, I'm only going to show you the pseudo-ESS from Lanphier. It really just considers rows in this distance matrix. For each row, treat it like it's a single variable and compute the classical univariate ESS. What Lanphier did was they reported the median and the 95% intervals. But ESS really is, I think, best viewed as a single measure, especially if you, say, wanted to run a chain until you get a certain ESS, in which case you're either interested in the lower end of that interval or the median. So what we're going to do is we're going to take two different estimators out of this. We're going to call one the median pseudo-ESS. That's just the median of these pseudo-ESSs. And the minimum, which is just the minimum. The minimum sort of is our conservative threshold, we might think, and the median is, well, hopefully a little more accurate in general. The other thing we're going to do is called the Frichet correlation ESS. This one is a little more involved. To understand it, we need to know that for a Euclidean variable, we can use the distance matrix to estimate both the variance and the lag-t autocovariances. What that means is that following along with the Frichet generalization from means and variances to Frichet variances and means, if we use any arbitrary distance on any arbitrary structure, such as trees and an RF distance, we can now compute Frichet variances and lag-t Frichet autocovariances. So by abstracting away to distances, we have a Frichet generalization of correlations. How do we do that? Well, it turns out that the variance can be estimated as the average of the upper, or if you prefer lower, triangular elements in the matrix, or half the average in total. The covariance, a little more involved, but only a bit. The covariance boils down into the variance in the first chunk up to the time lag, the last chunk after the time lag, and an average distance between trees at that time lag. And we put those three elements together as so, we can approximate the covariance. It would be exact, except we've omitted two other expectation terms, which for MCMC should be about 0. So this should be a pretty good relationship, a pretty good approximation. Now, of course, variances and covariances give us correlations, and we can plug this into our favorite ESS computation machinery. Okay, so like I said, we're going to test these measures in simulation. Like I said, also, we have found a way to convincingly, I think, fake phylogenetic MCMC that looks a lot like the real thing. We're going to use our testing procedure, our ESS and MCMC equivalency, to test how well we can capture the Monte Carlo variability in split probabilities, tree probabilities, and the summary tree. Now, we're also going to compare to standard practice, which is admittedly not the greatest. Two things you commonly see in the literature are ignoring the mixing of the tree, which I would say implicitly assumes that the effective sample size is the number of samples, and using some sort of proxy, often, almost exclusively, the univariate ESS of the log posterior density, which is also not great because that is pretty decoupled from the tree because posterior distributions contain many parameters, and so that's pretty far off on the mixing. Okay, what we're also going to do is we're going to try to make interpreting the difference between our two standard error measures a little easier. Instead of just looking at them, we're going to take a relative error, specifically the ESS relative to the true, or the Monte Carlo, Markov chain Monte Carlo. Just subtract and divide. The nice thing about this is twofold. One, this is comparable. This relative error can be compared across lots of different simulations. Two, it gives us a nice left to right axis. If we have if the RMC is greater than 0, we have overestimated the ESS. If the RMCE is less than 0, we have underestimated it. So it's pretty interpretable. We can also compute this in a normal standard use case of ESS. In fact, we're going to target a standard normal and do this a bunch of times and compute the RMCE, and we'll use that as a baseline for how good performance could be for our measures. Okay, I'm going to build up our results for splits a piece at a time. The results for trees and for the summary tree look pretty similar. All right, here are the tree ESS measures I've talked to you about. There are more in the paper. We're going to show them in rows, and here are the baselines. The x-axis is our RMCE. Here is 0, where we want, and our normal based benchmarks. So 50% in solid red and 80% in dashed lines. So not perfect, but on the nose. Here are the median 50 and 80s for the tree ESS measures. You can see the Fichet correlation and the median pseudo-ESS line up nicely. Medians are near 0, 50s line up with 50s, 80s line up with 80s. The minimum pseudo-ESS is very conservative. We have small RMCE, which means underestimation, and the benchmarks are, or the things people do in practice are likely to lead to overestimated ESS. For fun, here's all the points. And in the paper, you'll see figures like this for the tree probabilities as well and the summary trees. But they all have the same general pattern. Fichet correlation is slightly more conservative than the median pseudo-ESS. Minimum pseudo-ESS, very conservative. Benchmarks, not so great. So, are there effective sample size measures for trees? I would say yes. Specifically, there are tree ESS measures which can capture the variability in 3 important quantities: split probabilities, tree probabilities, and summary trees. One caveat is that the performance of all of these things, these estimators we tested, is best when it says the ESS is large, over 500. When the ESS is smaller, we get some bias in our estimates. We tend to underestimate the ESS, and the variability is much worse. So these do capture the Monte Carlo variability, but they do so best when the ESS is large, which shouldn't be a problem because your effective sample size should be big anyways. All right, all in all, I think that what I've shown you is that we can extend the effective sample size to non-Euclidean cases. Trees are but one of many, I think, that we could do this for. Low-dimensional representations, especially via the distance matrix, seem to be quite effective. I've shown you how we can test the efficacy of these measures. So as we move into trying to compute ESSs beyond Euclidean variables, we can make sure that our approaches work. For phylogenies, I've shown you that these ESS measures capture things that we care about, or at least that you care about when you're estimating trees. And all of this has been implemented in an R package, and we've described it more fully in the preprint of the same name as this talk. In the R package, we have implemented the ESS computations generally. So anything you can feed in objects and distance computations, we can get an ESS for. The simulation-based approach is mostly on trees at the moment. And with that, I thank you for your time.